All right, let's talk about how you actually compute square roots, cube roots. Um, so there's the simple way, which is basically you have a calculator, the square root function, square root 2, done. Easy peasy, right? There's also 2 raised to the 1/2 power and 2 raised to 0.5. All right, that'll give you square root 2. And you can type in anything you want. That's the square root of 5,000, no, sorry, square root of 56,824. It's 238.3778513, blah, 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 blah. Keeps on going, presumably. Well, definitely. But, so that's one technique, which is basically appeal to a higher authority, namely your calculator. Now, there are other ways, of course. It's a question of how the calculator does it. That is a question. Probably uses exponentials and logs, but that's for another time. There are ways for the calculator to do it without those things, as I'm about to show you. So we're trying to solve x squared equals 2. All right, so let's say I have a guess. Let's say I will guess x equals 1.5. All right, now obviously I can do 1.5 squared and I get whatever that is, 2.25, I guess. So that's, too big, right? But, and so then you can just take another guess. You could do 1.4, which comes out to be, I don't know, what is that? That's right, you just compute that out. 4, 5, 6. It is 196. Like so. And then you could say, okay, well, 2.25 is near 1.96, and I mean 2, so there's 2. It's very close to here, far away from 2.25, relatively speaking. So I could try 1.41, and then that'll be too low, and then 1.42, that'll be too high, and so forth. Just to demonstrate that, let's define this as x squared, and let's go to the table. So let's start with a guess of 1.4 and 1.5. All right, and so you got a little step size there, so we'll just go 1.41. So that's pretty close, 1.42. All right, so 0.02, 0.02, so it's kind of similar. So let me go with 1.1415. Too high. So what is this? Too low. So it's somewhere between 1.414 and 1.415. Right? And looking at this, it looks like it's closer to 1.414. So 1.4, what is it? 1 geometric is 4.14, like 3. What? Where'd that go? Oh. Okay, well that was pretty good. A little high, so 14142. And yeah, and so forth, right? So you can just kind of guess and check with almost no thinking. So that's kind of cool. what if you had a little bit of thinking? Well, that could be nice. So, a little bit of thinking. What is it? So, if our guess, like 1.51, 1.5, was the solution, then 2 divided by 1.5 would basically be equal to 1.5, right? Because 1.5 squared was supposed to be 2. It's a big if. It's not, so it doesn't work out, right? Instead, we have 2 and 1.5. 2 divided by 1.5, which is, well, 2 divided by 3 over 2 is 4/3, 1.33. Okay? And so the idea here is essentially we want to average the two. So 1.5 was above, and the 4/3 was below. And so we're just going to go with trying to get into that middle zone. Now, this isn't going to give us the right answer either. But, so average, our guess. Let's just call G as our guess. So we take G, and we add 2 divided by G, and we average those two things. All right, so that's our algorithm. So let's see how that works out. If I define, well, actually, I guess I could keep that squared, and then y equals is, what was it? It was x plus, say, 2 divided by x divided by 2. Now let's go to the table. So look at how this table has progressed, right? 1.4, well, let's start simply. Let's actually try, I guess, what happens with 2. If I try 2, what do I get? So 2, of course the square is 4, gives me a guess of, my next guess is 1.5. And so then 1.5, I plug that in, and I get 1.41666667. So I'm just going to do that. 1.41666667 or something. And so then that gives me a slightly better number, 1.4142. Let's try that, 1.41421569. There we go. Now I'm accurate to, like, what is that, 5 decimal places or something? And so now I try it again, 1.41421356. And that's basically, you're done at that point, right? Kind of flat lines. And if we go back to our home, 1.41421356 versus 1.41421356. I guess I'm missing a digit. And so that is how we can use that formula. And that just gets to any root. So if I go back and let's say I want to do the square root of 42, then I replace this 2 with 42, go to my table. Let's just clear everything out. So square root of 42, I could probably just try any old guess, but 36 is 6 squared and 49 is 7 squared, so it's going to be somewhere in between there. So let's just try a 6.5. That looks like it's a pretty good guess. And that looks like almost there already. 4.807407. And that's pretty much it. What is that, 2 steps? 3 steps? I don't know. That's crazy. It's a crazy good formula. What happens if I start it with 42? So that would give me a guess of 21.5 for the next one. And then 11.7, and 7.65, 6.57, 6.48, oops, sorry, 6.48, and then I'm basically done, right? So even starting at a terrible guess, 42 is a terrible guess for the square root of 42. It still is like, what, 1, 2, 3, 4, 5, basically six steps to get to the end. It's crazy. It's crazy. It's so good. So good. All right, so that's you got guess and check and got the average. One thing about these formulas that is well, yeah, so basically here's your formula: g plus the number divided by g over 2. So that's the formula where the number is the thing to get square root. Now, actually, what happens if something has an exact square root? So, oops, sorry, 9. So 9, square root of 9 is 3. So if I did that, of course, if I plugged in 3 for the answer, it just gives me the same thing to guess again. That's good. What if I tried starting with 9? 9, 81, 5, 5, 3.4, 3.023, 3.0008, and whatever that is. And it gives me 3. Now, calculator's round, so it actually gave me 3. If you were to actually do this thing by hand or something with more precision than this calculator, it would keep kind of going on. You would never actually get to your answer of 3. It just approaches it ever so closely. All right, so that's how to do square roots. I guess I should also mention some properties of them. Square root of, say, like 6 is equal to the square root of 2 times the square root of 3. That is the square root of AB is the square root of A times the square root of B. Basically, because when you square them, you get the same thing, right? Square, because AB is equal to which, you know, if you really want to do it out, right? Not that interesting, but the idea is when you express everything in the way that what it really means and use associative and commutative rules and whatever, everything just works out fine. So you can break up square roots of products. Square root of A plus B, no simplification in general. Right? So, I mean, there just really isn't. A canonical example for this is square root of 9 plus 16, which is the square root of 25, which is equal to 5. And if you were to somehow break this up, this is 3 and 4, which is 7, right? So that just doesn't work. And if you wanted to try some other crazy ideas, hey, try yourself out. I'm telling you, there's nothing that easy to do. There are some forms and things that maybe somehow is useful in certain contexts, playing around with algebra somewhat, but for the most part, sums are just awful to deal with square roots because it's not the natural thing that square roots are related to. Square roots are related to multiplication, not addition. Alrighty, so now you know how to compute the root of any number. Take a guess. Take the number you're trying to find the square root of, divide by your guess, and then average the two, because you got the two things. And then just keep doing that. I guess before we should finish off square roots, I should mention, just to be clear, so like square root of 2 was approximately what, 1.414, right? And so like if I wanted to do 1 plus the square root of 2, that's approximately 1 plus 1.414 equal to 2.414, right? If I wanted to do 2 times square root of 2, it's approximately 2 times 1.414, which is 2.828, right? If I wanted to do 5 times square root of 2, you know, I would just do it the usual way. 5, 0, 5, oh, sorry. All right, so this thing is 0 and let's see. Should end up with 5 digits, including possibly leading 0. So 0, 5, and then 4 times 5 is 20, so that's a 7. 0 and 5, 0, so that's 0, and then 5 and 2, 7, and 0. Then we got 3 decimal points. There we go, 7.07. Right, and that makes a bit of sense. 5 times 2 is 10, and so somewhat being halfway between seems reasonable, slightly less. It's all good. Anyway, so the way of dealing with arithmetic with square roots and stuff, at least in terms of getting approximations, is you approximate the roots and then just do the decimal arithmetic. If you wanted it to be precise, 3 plus root 2, that's exact. Right? There's nothing you can really do beyond that. Now there is something that typically in K-12 kind of settings, but sometimes it's useful elsewhere, is let's say that you have 5 over square root 2. Now of course you can approximate it by doing kind of like 1.41 into 5, so forth, but you know that turns out to be tricky if you want to add the decimals, because it's here, you know, like dividing is, you kind of want to make the denominator there natural number. So what we typically do will be multiply by the thing, the root, top and bottom, so we're just multiplying by 1, not changing anything. And we end up with 5 root 2 over 2. Square root 2 times square root 2 is 2. That's square roots for you. And so now you could compute, you know, 2 divided into 7.070, and you do that out. You know, 3, 10. Where's it? 5, 5, so that's 0, then you get 7, so 3, and then I presume it'll be 5 again. And if you want to increase the number of digits, increase the number of approximation of square root 2, and then multiply that by 5, and then do the division into 2 by that. And you can just kind of add on, right? And so, did I come up with 3.535? So let's try that out. So calculators don't care about dividing by square roots. So let's just do that. 3.535533906. Beautiful. And just to confirm, 5 times that, it's kind of normalization. Yeah, gives me the same thing. Okay, good. So that's a bit of computations with square roots. Oh, the other thing that I love to torture people with is, let's say that you were dividing 5 by 3 plus square root 2. Okay, that's kind of a mess. And this is still going to be a mess, but you multiply by the conjugate of it, 3 minus root 2. Okay, and so this is like 15 minus 5 root 2, all divided by, and when you multiply this out, this is the magic of it. So you have the square root 2, but you also have minus that, and then minus 2. Square root 2 times square root 2 is 2. So these two cancel, and then you get 15 minus 5 root 2 divided by 7. And that's something that you can now do by hand if you wanted to. And again, you can test that out. All right, so we get that. And then what did I say? It was 15 minus 5 square root 2. Oops. Divided by 7. Beautiful. See? So those are some of the tricks of playing around with roots and numbers. Really, if you want a decimal approximation of these things, just plug them into the calculator or Wolfram Alpha or whatever, and let the computer sort of deal with these things. It gets messy real quick. And the biggest rule of thumb with playing around with this stuff is that when you try to do some manipulation, always find a tool that you can check your starting point and your ending point, and that they actually are the same,